You build an automation script to route a single LLM prompt, and it works perfectly on your local machine. But the moment you expose that exact same logic to 10,000 simultaneous inputs, the entire architecture collapses. Consider a standard autonomous social media engine. We trigger a workflow in Notion, process the data through Claude 3.5 Sonnet to format text variants, and use make.com to push the output to X and LinkedIn. The entire pipeline executes in exactly 55 seconds. But watch what happens when an entire marketing team updates that Notion database at the exact same moment. The APIs hit their rate limits, the orchestration loop bottlenecks, and the system completely stalls. There is a persistent belief that relying on high-tier cloud endpoints like Claude 3.5 somehow shields you from writing efficient internal logic. It doesn't. System performance is bound by the structural constraints of the underlying logic. When a system chokes, the failure follows predictable patterns that can be measured before a single line of code is deployed. To measure that predictability, we use big O notation. This is not a calculation of the absolute seconds a task takes to run, and it does not track the exact bytes of RAM consumed by your machine. This chart shows exactly how a system degrades under pressure. Big O measures the curve of execution time scaling as input size approaches infinity. We will map our AI social media engine, Notion, N8N, and make.com onto this grid to visualize core computational complexity classes. We will examine each stage of the engine to see which complexity class it occupies. These specific curves determine whether the system can handle a sudden spike in requests or if it will fail under the load. Mastering these curves is the mandatory threshold for transitioning from piecing together no-code tools to engineering highly resilient, scalable systems. Let's isolate milestone 1 of our engine, the input trigger firing from the Notion database. If you configure an orchestration tool to pull that database every 5 minutes to check for new items marked approved, you are burning computational cycles checking for data that might not even exist. This chart shows a flat line mapped as O of 1. By using a direct webhook, the workflow triggers only when approved, achieving constant time execution. The computational cost remains flat, processing instantly whether the database holds 10 or 10 million items. Now, compare that to milestone 4 of the engine, where the make.com confirmation loop verifies live URLs. Imagine the system must verify a specific post status by scanning an unsorted chronological log of every single URL it has ever published. This chart shows linear time, or O of n. The time required to complete that scan scales in perfect one-to-one parallel with the total number of posts. While the webhook trigger processes instantly no matter what, the verification log scan grows increasingly heavy and slow with every single post added over the lifespan of the system. ON logic is acceptable for minor administrative tasks, but deploying it in the critical path of a high-volume data router guarantees inevitable latency degradation. This diagram maps an LLM orchestration engine querying a distinct memory database cluster. We're pivoting from multi-platform routing to the core requirement of any AI assistant: persistent chat context and memory retrieval. If you query a massive, unstructured database for a specific past conversation using that linear O of n logic, the search will drag out until it triggers API timeouts. The architectural solution is indexing. Indexing pre-sorts the contextual data, clearing the path for much faster retrieval algorithms. This animation illustrates binary search logic enabled by that index database. At every single step, the algorithm cuts the total search space exactly in half. This chart shows logarithmic time, or O log n. The curve rises quickly at the start, but then abruptly flattens out. Under O log n, doubling the total amount of memory stored in your database only requires one single additional computational operation to retrieve it. Without O log n indexing, building an AI assistant with deep historical context is computationally impossible at scale. Urgent danger zone, quadratic time, or ON squared. This is responsible for the majority of severe system crashes. Suppose you configure a flawed make.com router path. You set it to check every newly generated Claude 3.5 post against every single previously published post to catch duplicate phrasing. This nested cross-referencing compares every item against every other item. This multiplies the operation so rapidly that API rate limits are exhausted almost immediately. This chart illustrates the severity of ON squared. dwarfing our previous curves. An input size of just 1,000 posts now requires 1 million separate operations to complete. Let's shift back to milestone 2, where N8N interfaces with the Claude API. Here, we confront the ultimate engineering dilemma, the time versus space complexity trade-off. Option 1 is to maximize space complexity. You consume persistent database memory to pre-generate and store hundreds of X and LinkedIn content variations. Option 2 is to preserve that memory space, but drastically increase time complexity. You force the Claude 3.5 API to dynamically generate those variations on the fly for every single request. There is no perfect universal answer. Elite systems architecture is the act of deliberately choosing which complexity trade-off your specific infrastructure can afford to absorb. This macro view shows the fully deployed N8N, Make.com, and Notion AI architecture functioning continuously under high load. We can now place our master cheat sheet next to the architecture. The engine executes its 55-second loop specifically because each milestone was intentionally engineered to avoid the pitfall of high-complexity classes. These same principles dictate the structural difference between contiguous memory logic and linked memory logic when designing how an AI assistant retrieves its historical context. Modern orchestration platforms make it dangerously easy to ignore underlying data structures because the user interface hides the algorithmic cost running beneath it. Claude 3.5's processing speed cannot compensate for an underlying data pipeline that mathematically scales toward infinity. Designing for scale requires grounding every integration in these mathematical principles. High-performance systems are built on the efficiency of the underlying engine.